Welcome back, calculates, to logarithmic differentiation. So we're going to start out with implicit differentiation. Remember, that's when it was too hard to get y, by itself. And so I notice, oh my goodness, x and y, look at them, they're mixed right here. Multiplied together, I'm never going to bust that away from the y, so I can't get y by itself. So what I do note, though, is that I could separate that product into addition. That's okay to do using my log rules. And now it'll be very easy to go through and do the derivative of each term. Remember, I'm doing every term with respect to x. So this first one, the derivative of natural log of anything is 1 over the anything times derivative of the anything. Well, the derivative of that is 1. As a matter of fact, it's dx dx, which is definitely 1. And then the derivative for this piece is 1 over y times the derivative of the anything, which is y. And the derivative of this with respect to x is just 5. And the derivative of this with respect to x is 0. And so, of course, I want to get I want to get dy dx by itself. So now I have to start moving some things around. And I don't need this. So I'll move this over, I'll subtract it, I'll move this over. So I'll have 1 over y dy dx equals negative 1 over x minus 5. And then if I want to get dy dx by itself, I can multiply both sides by y. So poof! And then dy dx is equal to negative y over x minus 5y. And of course I could, get a common denominator and actually add them if I want. It would depend on the multiple choices. So just a quick recap what you know in mathematics. If I had a problem that said that show that 4,2 is a solution to the equation, and I asked you how would you show that, hopefully your response is, well, I would plug in the point and see if it worked. And that is exactly what we do. And of course we end up with 0 equals 0, so voila, it is a solution. So I want to do this for the next problem. I want to show that this is a solution to this equation. Well, if I'm going to plug it in, I need to have a y prime, and I need to have a y double prime, and then work off of that to see what happens. So let's start with y prime. So if I take the derivative, I'd have 2 and then times 1 over x times the derivative of the stuff I'm taking natural log of, which would be 1, and then plus 0. So really this is just 2 over x. And then if I take y double prime, so I got to take the derivative of that. Well, let's see, that's, I could write this as what? 2x to the negative 1. So if I take the derivative, I get negative 2x to the negative 2 by powering down, which is negative 2 over x squared. And so now I have both y prime and y double prime, and I can plug it in to my equation, and we'll see if any magic happens. So over here I'll have x times negative 2 over x squared, because that's y double prime, plus 2 over x, because that's y prime, and I'm checking to see if it equals 0. And I think I can do some simplifying here. Pair of x's will cancel. So I'll have negative 2 over x plus 2 over x, and oh my goodness, it works. Therefore it's a solution. Now, one of the neat features of using logarithms is it can start to bust things apart that's difficult for me to get apart otherwise. So looking at this equation, I go, good grief, could we possibly put anything more underneath the square root? And so I'm going to take natural log of both sides. So I have this big square root. And then the minute I do that, I say, wait a second, I could write that as all of this stuff to the 1/2 power. And the minute I do that, since the power is only on the stuff, I'm allowed to bring that down in front. And now I have a product, and I'm allowed to separate product into some addition. So I'm going to separate those pieces, those product pieces, all into their own separate logarithms, but they're joined by addition. And so now, when I take the derivative with respect to x, I'll have 1 over y, and then dy dx. Remember, I have to take the derivative of the stuff. So 1 over the stuff times derivative of the stuff. And then that coefficient is going to hang outside. So I'll have 1 over the stuff times derivative of the stuff, and 1 over the stuff times derivative of the stuff, and 1 over the stuff times derivative of the stuff. And so when I simplify, of course, I'll want to get y by itself, excuse me, dy dx. Why do I keep saying y? So my derivative, I can call it y prime at this point if I want, is 1/2. And then each of these fractions, of course, I could get a common denominator, but it's going to be a lot of work. Again, going to be dependent upon multiple choice. And then times y, but I don't want y over here. I need everything in terms of x. But I know what y is in terms of x. It's all the way back up here. Look, that's what y is. So in place of y, I know what his x substitute is. So I'm substituting it back in. Isn't that the scariest answer you've ever seen? Now we've probably seen scarier.